Welcome back to another LeetCode video. We're currently looking at graph problems, going through the list of graph problems from the LeetCode 150 list. And the next problem I want to look at is surrounding regions. And surrounding regions, I have solved this before, but yeah, 3 years ago, roughly. All right, so yeah, let's see if we can solve this one shot, and I hope we can do that. Let's have a look. So we're given an n by n matrix board containing letters X and O. Capture regions that are surrounded. Okay. Connect. A cell is connected to adjacent cells horizontally or vertically. Right? A region. To form a region, connect every 0 cell. Surround means surround the region. A region is surrounded with X cells if you can connect the region with X cells and none of the region cells are on the edge of the board. Interesting. So to capture surrounding regions, replace all zeros with X in place within the original board. So you don't need to return anything. All right, I guess that's kind of cool. I think this is just a variation of exploring islands, right, that we've done before. So I think we can one-shot this quite easily. Let me just take this example and we have a look at this here. Let me make that a little larger so I can draw on it. And yeah, so we have this thing. Anything that is not connected to the edge will be wiped out, right? So this one, that one, and this one, and then this remains. I think what we can do is we could, use BFS, breadth first search, and we started with all the cells that are landmasses that are actually on the edge of the grid. So, well, we would add this cell to it, and then we start exploring into horizontally and vertically connected land regions. And every land region that we can touch is not going to get deleted, but any land region that we can't reach, like those ones, they will be deleted, right? Because they don't belong to the ones that we've discovered. So if we would say that we have, if we had an O here instead of an X, we could explore all of these cells and none of them get deleted. Does that make sense? I think it does. And so we really just have to iterate over the first row, the bottom row, the first column, and the right side column. All of these cells will be in our little BFS queue. So that'll be all the elements that we put into it. And then we just start to iterate over, all of the elements and explore the island. So we're going to need a way to prevent going backwards. And with the BFS, we probably use a visited set that tells us whether we've visited a node before or not. And we also need to, we need to figure out what are the neighbors of a cell, right? If we have any cell where there's 0, how do we get the left, right, top, bottom neighbors? So that'll be another little helper function that we have. We will also have maybe a method to explore the island and a method to delete landmasses. Exploring means just we're going to, this is going to be the exploring part. Deleting landmasses is then basically remove any O from the grid that is not part of our visited set. That's going to be it. So in terms of time complexity, well, we're going to visit every node at most once in the worst case. That is when every node in the grid is 0. So it's n by m time, meaning width times height of the grid time. In terms of space, it's the same because we need to keep track of the visited set. So yeah, that's what we're going to do. And that should be straightforward to implement. So we're going to have a little helper function def get neighbors, and we pass in a position, neighbors, and we just constructed as an array of neighbors, return neighbors. If you've seen the other videos, you know that this is actually pretty easy and kind of repetitive a mechanic at this point. So we're going to use tuples for the position, but we still need to have access to the X and Y position. I like to pull them out like so, of course, and then we do for next X position, next Y position in, zip, and we're going to have two lists in parallel that we're going to iterate over. And here we're just going to put in x minus 1 for the left position. We're going to put x for the position above, x plus 1 for the position to the right, and x for the position below. Now we just need to have the matching y coordinates. So if x is minus 1, y position remains y. If x is same as before, we look at y minus 1, and so forth and so forth. So that is how we do get all of the different positions. Left, up, down, left, top, right, and bottom of the current position. Now we have to do our little checks. So if nx f0, well, if nx smaller than 0 or nx larger than the width or equal to the width of the grid, and we're not going to be interested in exploring this because we are stepping out of bounds here. So we need to do the same for the y coordinate to make sure we remain in the grid. We also need to define our width and height here in a second. So let's do that right here. Width, height equals, well, the width is the length of the first row of the grid, and we get that this way. And the height is basically the number of rows in the grid, and we get that this way. Cool. So next, what we're going to do is, well, we're going to check whether we're looking at an x and an y, because we're not interested in water neighbors. So we're only interested in land neighbors, right? So what we're going to do is we're going to check if grid at position ny and x, right? Remember, first we pick the row, then the column. If that is equal to, well, what is the x? X represents, well, I'm talking about land and water because I did the island problem before. And in my mind, O means land and X means water. So if it's water, we're just going to ignore it. We're just going to ignore this. And we only want to explore the O's, right? And then, yeah, well, pass all the checks. So we're going to expand or append this to our neighbors array. And we're going to append the tuple of the next X and of the neighbor X and neighbor Y position. Okay, cool. So that's our little helper here. Now, the other thing we need is we need to, well, seed our queue, right? And what are we using for a queue? Well, I'm a big fan of the deck for depth first search. Sorry, breadth first search. And we're going to import this here from collections. That's the deck is the FIFO in Python. So from collections import deck. There you go. And we're going to, well, we have to fill it. Well, and as, like I said, we're going to fill the top row into our seed. So maybe do it like so. We first compute the seed def, get seed, right? And then we will compute the seed in a helper method. Maybe that's a little cleaner. Right, and then we'll just do, well, get seed to initialize our little queue for X in range, well, width. And we want to add all the cells from the first row to it. So seed, append, and we're dealing with tuples. So we're going to put in X and Y position 0. We'll do the same for the last position. So at height, sorry, for the last row at height 0. And we're also going to do this with the left and right column, right? So for Y in range height. And then we're just going to append, well, at X position 0 and at height and at, well, width minus 1 and height. So we're actually adding the corner cases twice, but doesn't really matter. Makes no difference whatsoever for the algorithm. So we're getting the seed here. Nice. Look at the structure. Isn't that beautiful? Isn't that absolutely wonderful? Well, now what do we do next? Well, we have to understand, well, we have to explore all the regions that are connected to the edge, right? So let's see. A region is connected. How do we name these things? Because maybe we can have a little helper function. Def capture regions. That is, capturing the region is like removing the part in the middle. Surround the region. To capture a surrounded region, replace blah, 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 blah. So how should we call this method that explores all the landmasses that are connected to the edge? Well, maybe we should say visit uncapturable regions. Right, that's exactly what we're doing here. And well, we can build a little queue in here, and we're going to use a little visited set that will return in the end. So we have to implement, you know, the breadth first search in here, right? So we'll have a little loop while we have elements in our queue. Well, we need to do some magic, and then in the end we're going to return the visited stuff. Now, in terms of the algorithm, what we'll do is, well, we will return the safe regions. So that's what we will do. And then we need to iterate over all of the cells in the grid again to determine which ones we can capture, right? So we'll have a little loop for y in range height, for x in range width, if so position equals, well, we have to create a little tuple so we can check whether it exists in our visited. If position in safe regions, we're going to continue. We're going to ignore it. Well, we're also going to check whether it's an x or an y, right? So if grid at position y x, well, if that's equal to an O, that's the only time when we're interested actually in looking whether it's a region we can capture or not. So we check if, well, if it's an x, we don't care, right? That means in Mamet, so it's water, it's blue, right? So there's nothing to capture there. Now, if it is an O, that means it's maybe this cell or that cell. And if it's not part of the safe regions, so the regions that we could reach from the edges of the grid when we try to explore from there, if that is not the, well, if that is if the position is in the safe region, well, we can capture it. Otherwise, we can, and that's exactly what we will do. We will actually mark this in the grid with an X. There you go. So, and we return, I guess, the grid in the end. Probably don't even have to, but I'm just going to do it anyways because we're modifying the grid in place. So now let's flesh out our BFS here. So our queue, well, what do we do in the queue? We have to iterate over all of these neighbors. So what we will do is, well, for in range length of the queue. So we're going to take one step from every cell to the neighbors, and we'll do that repeatedly. So yeah, so what we'll do now is we pop out the next position, q.pop left, right? We remove the element from the FIFO, meaning the oldest one, which is at position 0, and that gives us that element in constant time, right? So now for npos in, well, get land neighbors. We already have that, isn't that nice? And we just have to pass in the position, and we just add them to our queue next to the neighboring position. That is almost it. It's not quite it. So we have to check if pos in visited, right? Well, we don't want to go there again. Otherwise, we'll have an infinite loop. So we're going to continue and ignore that. Otherwise, we're going to add it to visited. Right. So that should be everything. I probably have some typos somewhere. Let's figure out if we do, and hopefully the logic checks out. I think our approach is sound, even though we might have some smaller issues here. So cool. So we need visit uncaptured region. There was a typo there. Let me see. Grid is not defined. Why not? Oh, it's called board. Oh, fix that by renaming it to grid. Oh yeah, it's board, not grid. It was grid in the other example. So, okay, let's have a look at this. So we have a problem. Houston, we have a problem. So we are giving this grid, and we're not marking them as access when it's a safe region. Right. So the first thing that I'm suspecting is that I'm doing something wrong when I compute the neighbors. So nx, ny. So that's what I'm going to check first. -1 plus 0 plus 1 plus 0. 0 -1 0 plus 1. So that is correct. And x and y. If it's already a grid, we're going to ignore it. If it's not a grid, we're going to append it. And x and y, right? You only wait. Yeah. We're only interested in cells that are marked as an O. So that's correct. I think that is correct as well. If the position is in our visited set, we're going to not continue. Visit uncapturable regions. Maybe I'm having a mistake doing the initialization. The x is over the width, y is over the height. Seed append 0y with mine. So that also looks correct. Okay. Now, there's a problem somewhere here. Let's just print the queue. I just want to know what is in the queue. In the queue, we have all of these cells. Well, what we could do is we could simplify it maybe a little bit for debugging output. If we add the seeds, right, we can also verify whether it's a land or not. So if we could do that. We could filter out the ones to make it a little bit more legible. But I don't think we need to. Let's not do that. It'll make our code more convoluted. So let's focus on the debugging instead. Right, so that's in our deck, all of these cells, and we're going to, I see. So maybe something that we should do, well, we're not checking whether it's actually an O, right? So we put everything from the seed into it, but we're not checking if it's actually land or not. So we should add that, right? So if, and again, we do it x, y equals pos. So if grid at position yx is not an O, well, we're going to continue. Because that means we're not interested. We're treading water here. So let's see if that changes anything. And it does. Interesting. That's very interesting. Oh yeah, I understand now why. Because if we put in a cell that is already an X and then a neighbor is an O, it suddenly becomes part of the capturable region. So yeah, so we actually have to make sure that we also put only valid things in there. Or we perform this little check here. So I think that fixes the approach. Let's submit it for final testing. And all of the test cases pass. Very nice. So yeah, that's this approach. Easy enough. Yeah. It's very similar to the other problems that we had about number of islands, max area, rotting oranges, even Pacific Atlantic water flow. So that checks off another one from the list.